Okay, last section in chapter 2, section 2.7, inverse functions. The basic concept of inverse functions, they undo each other. Marriage and divorce, adding, subtracting, multiplying, dividing, those are all inverses. But not all functions mathematically are going to have inverses. Only a certain type of function is going to have an inverse. And that type is going to be a one-to-one function. A function f of x is one-to-one if a not equal to b implies f of a does not equal f of b. Now what that means, and it's right here, that's the same thing as saying that different input values, different domain values, different x values result in different answers, different output values, different y values. So a function is one-to-one. If I put different x values in, I will get different answers, and your answers are always your y coordinates. So different x values must result in different answers, different y values. Then that function is one-to-one. Now, proving that a function is one-to-one algebraically by writing down a bunch of x's and y's and numbers can be a little more difficult than what we really need to be doing. So we're going to do it graphically. We're going to use the horizontal line test to determine whether a function is a one-to-one function. A function f of x is one-to-one if there is no horizontal line that intersects the graph of the function at more than one point. Now you may remember from earlier when we did the vertical line test. The vertical line test told us whether a graph represented a function. Vertical line test said if a vertical line intersects at most in one point, then whatever graph you're looking at happened to be the graph of a function. Here the horizontal line test is saying, okay, you already have a function. We already know it's a function. Now that particular function will be this thing called a one-to-one function if any horizontal line intersects at most one point. And the fact, a function f of x has an inverse if and only if f of x is one-to-one. So if a function is one-to-one, it has an inverse. If a function has an inverse, it's one-to-one. So finally, the first problem here. Which of the following graphs represent a function that has an inverse? Now that is the same thing as saying, same as asking, which are 1, 2, 1. Which would be the same as our thing, same as which passes the horizontal line test. Okay, so I'm going to take my little red pen here. Horizontal line test says that I have to be able to draw a horizontal line and intersect the graph at most once. And if I go right here, it doesn't matter. Notice we intersect twice. So it intersects twice. So not one-to-one, 1-1, no inverse. Now here's what the horizontal line test is picking up. Remember we said one-to-one was different x's have to give different y's. And if we look right here, this looks like maybe that point there would be 1.52. And same thing over here, this looks like it'd be negative 1.52. So here, negative 1.52, over here, 1.52. Negative 1.5 an x-coordinate, 1.5 an x-coordinate, different x-coordinates, but yet they both had the same y-coordinate. And so it's not one-to-one. One-to-one means each x will have its own y value. No sharing of y values. So that's not one-to-one. So the first thing we know, since we know that's a parabola, and parabolas come from quadratics, we now know that quadratic functions are not one-to-one. Now if we look over here, look, any one-to-one function intersects intersects once. Right there, it might look like it's going to intersect most, but it's more than one. That's not. It's just we're not getting the resolution. But any horizontal line intersects at most once. So it is 1 to 1. So there is an inverse. So that's all there is to a 1-to-1 test. It tells us whether something is 1 to 1, or tells us what, or that's all there is to the horizontal line test, which then if it passes the horizontal line test, the function is 1 to 1, and if it's 1 to 1, it has an inverse. Okay, talking more about these things called inverses. Okay, we said earlier that the basic concept is that they undo each other. But mathematicians are going to be way more precise than that. So here's our definition. Let f and g be functions such that f of g of x equals x for every x in the domain of g, and g of f of x equals x for every x in the domain of f. Then f and g are said to be inverses. Here is the mathematician's way of saying that things undo each other. They use composition. Remember, composition is that idea of one function inside another, or using two functions sequentially, right on top of each other. And so what this definition is saying is I'm going to start with some number called x. I'm going to do whatever g does. Then I'm going to immediately do whatever f does. And then notice I get back to x. I get where I started. That I started with x. I did whatever g did. And then f undid g, getting me back to x. And then it has to be, to make mathematicians happy, you have to be able to do it in whatever order. I started with x. I did whatever f did, or whatever f does. Then I did g, and I got back to x. That I started with x, I did f, and then g undid that, and I got back to x. So there is the mathematician's way of saying that two functions undo each other. They use composition. Now, notation, the inverse of f of x is denoted by that symbol, and that is read f inverse of x. It is not an exponent. I know it looks like an exponent, and if it were any other number, it would be an exponent. But we use that -1 in that notation to denote inverse. That is what it means. And so then, because we now have this notation that that means inverse, then it's just a fact. When I compose f inverse with f and f with f inverse, because they're inverses, their compositions always have to kind of undo each other, kind of cancel each other, and we get back to x. Now let's note, that symbol, f inverse of x, does not equal 1 over f of x. It's not an exponent. It's our symbol to denote f inverse. The symbol f inverse of x always means the inverse of the function f of x. If for some reason you wanted to write 1 over f of x with an exponent, you would put the whole function in square brackets or parentheses. That doesn't really matter. I like square brackets. Put it in square brackets and then a -1. But that symbol is never 1 over f. And that's important to remember, because any of you that have to go on to trigonometry or calculus, if you misinterpret that symbol, all sorts of bad things happen. Okay, for next example. Determine if the given functions are inverses of each other. When it says that, what we have to do is we have to show that f of g of x and g of f of x both equal x. If we can do that, they are inverses. So let's start with f of g of x. So we think back to the last section, start on the inside, replace g of x with its formula. So my first step there, replace g of x with its rule of 2 over x minus 4. Then we use f's rule, replacing all the x's with whatever I have in parentheses. So using f's rule over here, 4 over x. So 4 over 2 over x minus 4 minus 2. So use F's rule of 4x over 2, replacing the x with whatever I had in parentheses, in this case, 2x minus 4. And now we simplify. So simplifying, and let's recall that a fraction means nothing but division. So that first guy would mean this, 4 divided by 2 over x minus 4, minus 2. Fractions mean nothing but division. That's all fractions mean, division. Then somewhere in elementary school, you learned that the way we divide fractions is invert and multiply. Keep simplifying. The 4 and the 2 cancel, leaving 2. And then that 2 I'm going to distribute. And so I get 2x minus 8 minus 2, which equals 2x minus 10. And so we can actually stop there. That is not x. Actually, let's summarize. And obviously, it's not x. And so putting it all together, so f of g of x equals 2x minus 10. That's what we came up with. And that is not x. And so we now know. So f and g are not inverses of each other. Now we're going to go ahead and get the other composition just for the practice. But if all you wanted to know was, are these guys inverses? You now know they're not, because that didn't turn out to be x. Now, just for the practice, let's find g of f of x. And let's recall that f of x equals 4 over x minus 2, and g of x equals 2 over x minus 4. So g of f of x, start on the inside, and I replace f of x with its rule. Then I use f's rule, or use g's rule, replacing the x with whatever is parentheses. So g's rule, 2 over 4x minus 2 minus 4. And so this is going to look like a horrible, horrible thing, but we will get it simplified. So here, use g's rule of 2 over x minus 4, replacing the x with what I had in parentheses there, 4 over x minus 2. Now our next step will be simplify, and we will start simplifying on the next video.